Area of polygons. In this lesson, we will verify the formula to get the area of the common polygons that we see in math. And these are the square, rectangle, triangle, and trapezoids. And we will verify those formula using definite integral. The area of a square with side A is equal to A squared. If this is the side of our square, the area of this bounded plane region is equal to A squared. For a rectangle, it is equal to A times B. For a triangle with height h and base b, so this one is a right triangle. The triangle that I will show you is a right triangle. But later on, we will verify this formula for both a right triangle and a general triangle. If this is our height and this is the base, the area of this triangle is 1/2 times base times height. For a trapezoid with bases A and B and height h, this is the area. You can look at 1/2 times A plus B as the average length of the bases, A plus B divided by 2. And so the area of this plane region is going to be 1/2 times A plus B times h. Verify the area of a square using definite integral. If our square has side whose length is A, we know the area to be A squared. We will draw this square in our rectangular coordinate system. So it's like, let us place our square in standard position. So we will place it in such a way that some of our vertices will lie along the coordinate axis. Because when we do it that way, the coordinates of your vertices, some of those coordinates will contain 0. And it's easy to do the computation when you are working with 0. Define the function that bound the plane region. So this function is bounded above by a constant function. F of x is equal to a. The interval of integration is from 0 to a. Let us now set up the definite integral. The integral of a dx evaluated from 0 to a. The integral of a dx is a times x. Evaluated from 0 to a will give you a squared square units. Area of a rectangle. Let us verify the area of a rectangle with length a and width b. We know this area to be equal to A times B. We draw our rectangle in standard position. Again, we must place some of the vertices along the coordinate axis. This will make our computations so much easier. So our region is bounded above by a constant function. F of x is equal to b, and b happens to be the width of our rectangle. Our interval of integration is from 0 to a. So the integral is the integral of b dx evaluated from 0 to a. And that is equal to b times x evaluated from 0 to a. And that's going to give you a times b square units. Area of a right triangle with base b and height h. We know that area to be equal to 1/2 times base times height. We begin by drawing our right triangle into the rectangular coordinate system. So it has a base whose length is equal to b and a height that is equal to h. And so that means this one would have coordinates 0h, this is the origin, and this one would have coordinates b0. Our plane region is bounded above by a linear function. Okay, a linear function whose interval is from 0 to b. This is a line. And you know how to produce the equation that define a line. So here we are already given the intercept. So we can produce the intercept form, the slope intercept form of your function. This is the intercept. That is where this plus h comes from. And the slope is equal to change in y over change in x. It's equal to negative h over b. And so this is our function. Our plane region is bounded above by f of x is equal to negative h over b times x plus h. The interval of integration is from 0 to b. Let us now get the definite integral. So the area of this triangle, okay, right triangle, is equal to the integral of our function, linear function, negative h over b times x plus h dx evaluated from 0 to b. This is just a linear function, a constant function, and this is the antiderivative, okay? And then we evaluate it from 0 to b. That will give you this one. The area is equal to 1/2 times h times b, which is what we expect to get. This is how we obtain the area of a right triangle. What if we are no longer working with just a right triangle? So our triangle is a general triangle whose base is c and height h. Something like this, for example. So what we do here is we will cut the plane region into two. A sub 1 and this one is a sub 2. We will get the area of each of those plane regions using definite integral, and then we will get the sum. So this one is bounded above by your function defined by this, h over a times x plus h. Again, I hope that you won't walk away from getting the function that defines that curve. That is just a linear function. And we began analytic geometry by studying the properties of lines and the various equations of a linear function. And this region is bounded by this function. Again, we will cut the plane region into two. This is a sub 1, this is a sub 2, and then we will get the sum. Okay, so the area of the first plane region is equal to this. The area of the second plane region is equal to this. Get their sum. So getting the sum, the common factor is 1/2 times h. 1/2 times a plus b. And if you were to look at a plus b is nothing but the base of your triangle. So 1/2 times c is a plus b times h. The area of a trapezoid with height h and bases a and b is given by this. 1/2 times a plus b times the height. So the bases here are this one and this one. Okay, so we can look at this to be our a and this one is our b. And this is our height. Now, if we will put this in our rectangular coordinate system this way, okay, this is the orientation, you will have to produce two functions, okay, and two definite integrals. Okay, one is from 0 to a, okay, 0 to a, and then you will produce another definite integral, and the interval of integration is from a to b. So two integrals. This is not the only way to draw your trapezoid in our rectangular coordinate system. And in fact, if we are to draw it this way, our integration is going to be simpler because now our plane region is bounded only by one function. And so this is the origin, okay? This is the height. So we are not accustomed to seeing a trapezoid this way. We are more accustomed to see a trapezoid drawn in this way. So this is the height, and these two are the bases. But now, if we are to draw our trapezoid in this way, these are the bases. This is A, this is B, and this is the height. So we need only to produce the function okay, that is above the plane region, and that is equal to this. Again, that is slope-intercept form. The y-intercept is a. The slope is change in y, b minus a over change in x, h minus 0, and that is the slope. So to get the area of that trapezoid is just getting the definite integral of a linear function from 0 to h. Okay? And this is straightforward. This is equal to, the area is equal to b minus a over 2h times x squared plus a times x evaluated from 0 to h. We will simplify it, combine similar terms, and this is what we will get. The area of the trapezoid is equal to 1/2 times a plus b. Okay, those are the bases, the sum of the bases times height.